Okay, let's see. I'm going to get started here. Just a brief introduction. My name is Jason Biggs. I am a developer for the Wolfram language chemistry offerings, and I'm here to talk about the latest offerings for Wolfram language chemistry coming out in version 12.2. Yeah, and now is when I hit the stop video, and we just look at the screen. Let's see. So the title of the talk this year is Molecule Fingerprints and Visualization. This is because I felt that I should not use the same talk that I use every single year, new developments in Wolfram language chemistry. So I've added that here as a talk subtitle. And also, my manager told me either always include the abstract on the first page or don't include the abstract on the first page. I couldn't remember, so I've included an iconized version of the abstract here on the first page because I like to be funny. Let's see. So this is the outline slide. First, I will do a very brief history of chemistry in the Wolfram language that involves going from chemical data to entity value to molecule. There will be a brief look to the future. We have a new data structure available in version 12.2, and we will look briefly at the biosequence. Then we'll talk about molecule fingerprints, which I've spent a good amount of time working on, but is not fully ready for release in version 12.2. So this is going to be mainly a sneak peek of features to come. Then we will take a brief tour of some of the resource functions available for visualization of molecules. And then we'll finish by looking at the interactive molecule editor that is available in version 12.2, titled Molecule Draw. So let's first look here at the brief history of chemistry in the Wolfram language. So essentially in version 6, we got chemical data. We got element data, isotope data. There were all of these new functions to give access to curated data. And by curated data, I mean this is experimental data that's available from sources like NIST or PubChem, ChemSpider, or publications put out by the ACS. So there are certain entities in it you can ask, for example, for the combustion heat, for Henry law constants, for van der Waals constants. These are all experimental values that are not computable directly. So they need to be, that's what we mean by curated. And so that was in version 6. Then in version 10, we introduced entities, and this provides more unified interface to the knowledge base. So we, as I mentioned, we had chemical data, element data, isotope data. Well, the number of different types of entities, the number of XXX data functions would increase exponentially, but instead we introduced entity value. So rather than just simply the string representing the chemical, we now have these, we call them the yellow boxes, right? So this is underneath, when you look at this is entity chemical diphenylmethane. And so it is an object that represents this entity in our database. And you can access many of the same, let's see, so all of the same properties you could in chemical data plus many more. And there's a much nicer interface for accessing data on multiple entities, multiple properties, and different ways of presenting the data. Then came version 12, where we introduced the molecule. So the difference between a molecule and a chemical entity is that for a molecule, you're not relying on any database call. You're not relying on there already being an entity in the knowledge base. So this entity doesn't need to be in chemical data. It doesn't need to be in PubChem. You could have made it up. You could have been the first one to ever think of this molecule, and you write out its IUPAC name, and molecule will create a data structure from that. And then you can generate 2D or 3D coordinates and compute properties for it. This was introduced in version 12. And if you like, if you're curious, for the curious among the audience, you can see the entire design process, because that is something that that we've started doing. So it's so actually, if you look at for the very second episode of live CEOing, you'll find it was about chemistry, and we were deciding, do we want to do this as an entity or as a function? And we decided we wanted to do it as a function, and so that's how Molecule came about. And if you're ever curious about some of the decisions that were made, I recommend going to the tape. So, but now in version 12.2, we introduce the Biosequence, and this is not my area of expertise. This is developed in-house by John Castle, our resident expert on bioinformatics. So I highly recommend this presentation from the last year's tech conference representing biological sequence data in the Wolfram language. So using a biosequence, you can create an object that represents a particular DNA sequence, for example. You can convert that sequence into a peptide sequence by translating it, or into an RNA sequence by transcribing it. You can then take that peptide that you create and convert it into a molecule, if you like. It turns out to be rather large, and you can actually generate 3D coordinates and view it. This becomes, of course, this is a relatively small protein with only 197 atoms. So the act of generating 3D coordinates and plotting them becomes more difficult the more atoms that you have, obviously. Let's see. So that is Biosequence. I highly recommend it. It's available in 12.2 with a host of support functions. So now I'd like to talk briefly about a slightly esoteric topic that that I've become interested in over the past year. And so we have this new functionality that's not quite ready for the system context, and so it's hopefully will come out in the next version, but this is a sneak peek of the things that are to come. So the basic idea behind a molecule fingerprint is to take a molecule and convert it to a sequence of ones and zeros, otherwise known as a bit vector, depending on the presence of certain chemical features. Also, alternatively, you can make a count vector, keeping track of how many times those features are present in the molecule. So that's step one, to create a molecule into a fingerprint. Step two would then be to use various different distance measures to give an idea of the molecule similarity, how similar are two molecules. So the basic idea is that molecules that share chemical features are more similar than molecules that don't. And so the more alike two fingerprints are, the more similar the molecules are going to be. Well, of course, different types of chemical features lead to different types of similarity. And as a result, in the literature and in common use nowadays, there are many different types of fingerprints available. So the basic functionality, the basic idea here is that you would have a fingerprint function, which would return an operator that could then be applied onto a molecule to generate a fingerprint. Why does it need to be so convoluted? Because there are many different options available. So if we look at the input form of that, we see, so it's an RDKit fingerprint. It returns a bit vector. It's got various options, the minimum path length, the max path lengths, whether to include hydrogens, whether to include branched paths, how large do you want the resulting bit vector to be, whether to use bit bond types when generating the bits. And these are all vary from different type of fingerprint to, so the different options, there are many different options for every type of fingerprint. And so wrapping it all up into one interface here is quite handy. But it means that you first have to generate a fingerprint function and then apply it onto a molecule to get your fingerprint. So another function will be molecule fingerprint similarity. So that would take two molecules as an input and return a numerical value to represent how similar the molecules are. 0 being completely no overlap whatsoever, and 1 being saying they're basically the same molecule. Molecule fingerprint similarity would take options such as a fingerprint function and a distance measure. So another function will be molecule nearest, where you take a list of molecules and a query molecule, and then you return either the molecule that is most like the query or the n molecules that are most like the query. So it works very similar to nearest, except it uses the fingerprint similarity as the main distance function. So the most basic type of fingerprints would be substructure fingerprints. So these are where you generate a set of substructure keys, and then this predefined set of keys, you enumerate it, and then you set bits or counts in the fingerprint based on whether that feature is present. So the most simple feature set you can imagine is elements. So we know that water contains oxygen, so I can say molecule contains to Q molecule of water, oxygen. True, but it doesn't have sulfur. So with that in mind, we can define a set of common elements. And in general, you could do, this would be quite easy to do with all of the elements. So you could do element data, open, close, and generate all of them. But we don't need to do that because this is just a simple example so that we can actually look at the fingerprints. So we set these common elements, we define a molecule. Let's see, let's make sure these are evaluated. And then we could generate this fingerprint ourselves, this Boolean vector, by just asking, does the molecule contain that element? And then looping over them. And we get a vector of true, false back. We can look at another molecule and ask the same question, and we can get two different fingerprints. So these lists of true and false. That given the two Boolean vectors, we then compute their similarity. For molecule fingerprints, people often use what's called the Tanimoto similarity, which is equivalent to to 1 minus the Jacquard dissimilarity, which is a built-in Wolfram language function. So using this simple fingerprint with these common elements, we can say that these molecules are 75% similar. So to make this, so that was if we were to just do that using existing functions, but the whole idea here is to create a simple and efficient API for generating these functions. So we create a fingerprint function based on substructures, and we give the substructure patterns being the common elements. We generate the fingerprint function, then we apply that onto a list of two molecules, and it returns two bit vector data structures. And if you like, you can look at the documentation. This is a data structure, so these were introduced in 12.1. These have various operations. They're mutable, and yeah, they're fully documented. So let's see. There we go. You apply those to fingerprints. You can then visualize them. And let's see. Does this? Well, so those don't exactly scale here. But let's see. So this the ones and zeros tells you whether those features are present or not present. And so then if we wanted to compute the similarity from these fingerprints, we would find first the total number of bits between the two fingerprints, and then the total number of bits in common. So this is the bits that are set in both fingerprint 1 and 2, and this is the total number of bits. And when we compute that, we get the same value for the similarity as we did using the built-in Jacquard dissimilarity. Or we can, for efficiency's sake, we can feed both molecules to molecule fingerprint similarity and give the given fingerprint function. So we already defined this, and this is the substructure fingerprint that uses that list of common elements, and it returns the value of 0.75. So one more step would be to ask not just whether a given feature is present in a molecule, but how often does it occur in the molecule. So we can take those common elements and we can apply that to a molecule and count them. And so for this toy example, it essentially reproduces the chemical formula. We see there are 3 hydrogen atoms, 6 carbon atoms, 2 oxygen atoms, etc. Or we can create a fingerprint function and tell it instead of a bit vector, we want a count vector. And we apply that to the 2 molecules and we receive this back. So this is another form of a fingerprint. This is so this is a count vector. And so with a count vector, we can't use the built-in Jacquard dissimilarity. We instead use the resource function multiset Jacquard dissimilarity, which takes into account not just whether a certain feature is present, but how often it is present. So when you compute the number of bits in common for the previous computation, it takes into account how many of those bits are there in each of the molecules. And so we can use the multiset Jacquard dissimilarity, and we can get a value, and we see these 2 molecules are less similar now that we take counts into account. And as before, we can cut all of that out and call molecule fingerprint similarity directly and give it the fingerprint function, which is now defined to use count vectors instead of bit vectors. So we can take that a little bit farther by using a more sophisticated set of patterns. So in this case, we've got a list of 300 predefined functional groups. And these functional groups have a name and they have a given pattern. So this is what's called a molecule pattern, and it describes a carbon with 4 bonds to it, and 3 of those are hydrogens. And it is bonded to another carbon atom about which we specify much less. So that's the definition in a pattern of a primary carbon atom. Same with secondary, tertiary carbon, and on the way down. So if we look at a given molecule and ask which of those patterns are present, we see it might have, it's got a primary alcohol, rotatable bonds, certain keys for being tautomerizable. So let's see, so if we define that, so then you can, if you like, you can look to see where these substructures occur in the molecule. I think it's fairly neat there. So now that we have that list of substructures defined, we can define a fingerprint function based off of those. And we can get back a count vector from it, and it'll tell us exactly how many times we see those features in the molecule. And so that would then be fed to the same similarity function as before. So what we've seen so far are substructure key fingerprints, where you have a predefined set of substructures. But more commonly used nowadays are hash-based fingerprints, where the number of possible substructures is incredibly large. And so therefore, there is no attempt made to enumerate all of the substructures beforehand. Instead, you generate the substructures at the time of looking at a molecule, and then you use a deterministic hash function to take the substructure and convert it into an integer. And that integer tells you what bit you are setting. And then if desired, you can take that, that bit and fold it down to get a number commonly between 1 and 2048, or some other multiple of 8. So it results in a smaller fingerprint, faster similarity comparison, but it can also result in bit collision where two different substructures end up setting the same bit. So it has its drawbacks. So this is a common type of this hash-based fingerprint. So the substructure here is an atom pair. So look, so here we have two oxygen atoms with a vertex degree of 1, and they're separated by 4 bonds. And so that in and of itself is a substructure. Here we have two oxygen atoms, each with a heavy atom vertex degree of 1 and separated by 7 bonds. And so that is another type of substructure. And so when you apply this type of algorithm onto a molecule and generate all of the different atom pairs within that molecule, the common practice is to then take those atom pairs, those substructures, and hash those to a 64-bit integer. And then those are used as the keys in the count vector. It's also possible to use this in a bit vector form where you ignore the count information. So, right. So another type of common substructure is to use path-based fingerprints. This is a type of substructure that was popularized by the Daylight company. And so here, you generate, what you do is when you look at a molecule, generate all paths with a given length. And oftentimes that is a range. So for the RDKit fingerprint function, it will generate all paths between with a length of 1 or 7. And then from those, take those paths, look at all the atoms in the paths and atom properties and bond properties, and combine all that together to generate a hash that is then folded down to a bit between 1 and 2048, and you set that bit. And when you do that, it might set these min bits. Alternatively, if you set the min path length instead of 1 to 4, you set fewer bits. Circular fingerprints are a similar kind of thing where you, rather than all paths, you look at all substructures where atoms are a given length, a given topological distance from a particular atom. But it's the same type of action where you algorithmically generate all the possible substructures, take those substructures, convert it to a hash, and then set that bit. Let's see. So we can wrap this all up into a molecule nearest function. And I won't bother to evaluate this. It's fairly speedy, but we are running short on time. Essentially, you can, in this example here, we take a list of 2,000 molecules curated from PubChem by Bob Nachbar, and we convert those to molecules, and then we take a query molecule, and we try to find the most similar molecule to it. And so this example just shows that based on the different types of fingerprints, you can get very different answers to what is the nearest molecule to the query. So now I think it is time that I should skip on ahead to molecule draw, because it is the new feature and it's fairly neat, I think. So the idea here is that you can interactively create and edit molecules. And so you can add, modify bonds. We need more features, so hopefully more features will be to come. But essentially, so we start here with an empty palette. I select a single bond. I got it in there. I start adding more bonds. Now I can just come in and close the loop. If I don't like the way that it ended up looking, I redraw it. I can change one of those atoms to an oxygen, and then I can put a chlorine on that oxygen, and it should complain to me. It did. It highlights it in red because oxygen doesn't like having 3 bonds, unless, of course, it has a positive charge. So we add the charge and everything seems fine. And now we return that and we have a molecule. We could also do this on existing molecules. So first we use the optical recognition. We recognize this as a molecule and then we draw it. Right. And so we can go in here and start adding atoms. And then so that didn't quite work. So I'm going to need to figure out what happened there so I can undo the things that I've done, or I can redo them. And that is essentially the way the editor works here. I can delete bonds. Yeah. And so I think at 9:58 is a good time to stop the talk and move to the let's see, future directions. I want to mention this. We are looking at what to do next, right? New data structures, what enhancements to 2D and 3D plots. We want to add labels to plots, add custom R group labeling, custom styling. We're interested in looking at chemical reactions or macromolecules, having tighter connections to external sources. These are all things that that we are looking at, and if we welcome any feedback to help us prioritize that.